Hello, this is video 5 of a 6-video series on symbolic AI, interpretation and truth. So far, in propositional logic, we have been looking at formulas made up of symbols, built following rules in a mechanical manner. Now, to know whether a statement formula is true or not, to answer questions much as the brazen head did, we need to interpret them, to give them meaning, to give them semantic content. Propositional logic is great because we can formally define the notion of interpretation or semantic content of a formula. In propositional logic, there are two truth values, T for true and F for false. Notice that here I am using the same symbols for the constant T and F in our formulas, which is not a coincidence. Now, an interpretation I is a mapping from S to the set TF that assigns to every propositional variable a truth value, either true or false. To know whether a formula is true or false, we also give meaning to operators. We define how they behave. For example, to compute the truth value of the atomic formula Pope, that is a single symbol to express the fact that Gerbert is Pope, we need to know the truth value of the single propositional variable Pope. For example, I of Pope is equal to false, which means Gerbert is not Pope. To compute the truth value of the formula will be Pope and will die, we need to know the truth value of will be Pope, will die, and how the connective and behaves semantically. There, if both will be Pope and will die are interpreted as true, then will be Pope and will die is also interpreted as true, something that Gerbert failed to conclude. One way to define our basic operation negation, parenthesis, and or implication is to describe their behavior exhaustively, that is, to range over every possible interpretation of I and B. This is what is called building a truth table. For example, to define the negation, we give the value of not A for every possible value of A. If A is true, then not A is false. If A is false, then not A is true. Here, I give the truth tables of all our connectives. You can see on the first two columns that we are giving all possible truth values for the variable A and B. Remarked that some interpretations are peculiar and do not correspond to the usual interpretation of the words in a natural language. In English, when we use the word or, we typically use it as an exclusive or, as in, do you want coconut or chocolate flavored ice cream? We instead use the inclusive interpretation, where A or B is interpreted as true if at least one of the variables is interpreted as true. Finally, note that it is perfectly valid to define our own connectives. In this course, we use these specific definitions because they are common in modern logic literature. Now, we can easily interpret the value of entire formulas. Given the expression P equals Gerbert sings and not Gerbert at Jerusalem implies not Gerbert dies, and the variables assignment, Gerbert sings assigned to false, Gerbert at Jerusalem assigned to false, and Gerbert dies assigned to true, we determined that the interpretation of the old formula is equal to false, I, the interpretation of and the interpretation of not, false, implies the interpretation of not, true, which is equal to false, the interpretation of and true implies false, which is equal to false implies false, which is equal to true, according to our tables. If a formula has a variable assignment that makes it true, then it is said to be satisfiable. In general, it is computationally expensive in the sense that it requires computing time and memory to figure out if a formula is satisfiable or not. SAT solving refers to the research area that is interested in coming up with efficient algorithms for checking if a formula is satisfiable. Conceptually, SAT solving allows you to find if there is a solution to problems you can model using logic. For example, software verification to predict if a piece of code will fail at some point, hardware verification to check if a robot will fail at some point, planning for air traffic control, scheduling of sports tournaments,